Okay, I'm just going to jump right into it because it's long. I said to AI, "Hi, I was wondering, what do you think the strongest contributors to path loss are?" She said, "Path loss, the reduction in signal strength as it travels through medium, is influenced by several factors. Here are some of the strongest contributors: distance, blah, blah, blah. I'm trying to reduce a little frequency. Higher frequencies experience greater path loss. Obstacles, buildings, trees, hills, and other objects. Multipath propagation. Signals can reflect off surfaces, buildings around, etc., and arrive at the receiver from multiple paths. These multiple signals can interfere with each other. Atmospheric conditions, rain, fog, snow, and all these are very long. Terrain, obviously." And she said, "It's important to note that these factors often interact with each other. For example, the effect of obstacles is more pronounced at higher frequencies. Similarly, multipath propagation is more complex in urban." Okay, so then I asked, what are the biggest contributors to path loss at the lower frequencies? And then she says, "You're right to focus on specifics of lower frequencies. While many path loss factors apply across the spectrum, some become more prominent at lower frequencies." Duh. Here's a breakdown. Distance. Okay. I'm just going to try to cut this down because it's very long. Ground effects. At lower frequencies, the ground plays a significant role. Signals can reflect off ground. Multipath. Obstacles. Diffraction. While obstacles still matter, lower frequencies are better at diffracting around them. This is creepy. Okay, so it says, lower frequencies are better at diffracting around obstacles. This means they can bend, quote unquote, crawl around obstacles more easily than higher frequencies, reducing the shadowing effect. However, this type of obstacle matters. Dense foliage, okay, we know this stuff. Atmospheric absorption, heavy rain, man-made noise. I was kind of surprised that man-made noise would block these signals. That was odd. Okay. So I'm going to go, it's very, 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 very long, so I'm going to go to my next question. What is the mechanism by which, this is what I said, what is the mechanisms by which man-made noise would have such an effect on these low frequencies? Okay, and then she says, "You're right to ask about mechanism. It's not simply that noise is present, but how it interferes with desired signal at low frequencies. Here's a breakdown. Noise sources. Man-made noise at lower frequencies comes from various sources: electrical equipment, motors, transformers, power lines." Okay, we kind of know about all that. I'm going to keep going. Keep going. Yeah, that she had a very, very, very long answer to that one. Okay. Wow, she had a very in-depth answer to that. I'm still scrolling. Okay, so then I had to ask, what are the conductive materials they are finding successful? What are the filtration mechanisms used, to block these lower frequencies? And then she says, "You're asking about some very specific and important aspects of electromagnetic interference, EMI. Shielding. Here's a breakdown of materials and filtration mechanisms used. Conductive materials for shielding. Obviously, the key property of shielding, high electrical conductivity, as allows the material to reflect and absorb electromagnetic waves. Here are some of the most common and successful conductive materials," and I'll just shorten it. Copper, okay? Aluminum, okay? Steel, especially pre-tin plated, okay? Nickel, used alloys like new metal or mu metal for specialized shielding, okay? Conductive coatings and paints, all right? Carbon-based materials, emerging materials like carbon fibers, graphene, and carbon nanotubes offer high conductivity and are being explored for advanced shielding applications. Okay. Factors affecting material choice: frequencies. Different materials have different shielding effectiveness at different frequencies. Cost. Some materials, obviously. Weight. Weight can be critical, okay. Corrosion, yeah, we know about this. Formability, how easily the material can be shaped or molded. Filtration mechanisms. Filters are used to selectively block or allow certain frequencies to pass through. Here are some common types. Low-pass filters allow low frequencies to pass while blocking high frequencies. High-pass filters, blah, blah, blah. Band-pass filters allow specific range of frequencies to pass while blocking others. Band-stop filters block a specific range of frequencies while allowing others to build. Okay, so and she tells me how filters work. I know that. Okay, and let's get to my next question. Wow. She has so much to say. Important note, shielding filter. Okay. Okay. And then I said, really phenomenal information. I love discussing things with you. Thanks. You're very welcome. I'm glad you found this information helpful. I enjoy your conversations as well. And blah, blah, blah. Okay, and then I'm going to ask my next question. I'm starting to think that native processing units are the future. I've thought that light was a better method for a very long time. In the future, do you think that natural light from the sun will help or hinder this process? And then she says, you're touching upon some really fascinating and forward-thinking ideas. The concept of native processing units, especially those leveraging light, is definitely an area of intense research and development. Let's break down your question. Native processing units. The idea of native processing units suggests systems that more directly utilize natural phenomenon like light, as you mentioned, for computation rather than relying solely on traditional electronic circuits. This could involve photonic computing using photons, light particles to perform computations. This has the potential for much faster speeds and lower energy consumption compared to electronic computing. Quantum computing. Exploiting the principles of quantum mechanics to perform computations in a fundamentally different way, allowing for the solution of certain problems that are intractable for classical computers. Neuromorphic computing, mimicking the structure function of the human brain to create more efficient and adaptable computing systems. Light processing method. You're right to think that light has a great potential. Photonic computing offers several advantages. Speed, blah, blah, blah. Bandwidth, blah, blah, blah. Consumption, blah, blah, blah. Okay. Now, about the sun's natural light. This is where things get interesting and complex. Potential benefits. Energy source. The sun could potentially provide clean, abundant... Okay, we know all that. Okay. Challenges. Variability. The sun's intensity varies throughout the day with weather conditions, blah, blah, blah. Coherence. Sunlight is not coherent like laser light, which is important for many photonic computing applications. It's a mix of many wavelengths and phases, focusing and directing. Effectively capturing, focusing, and directing sunlight for precise computing options would be a significant engineering challenge. And then she says, my perspective, in quotes, in parentheses, as an AI, while using the sun's natural light for native processing has certain appeal, technologically hurdles considerable. It's more likely that near-term advancement in photonic computing will rely on controlled light sources, lasers, LEDs, rather than direct sunlight. However, the long-term potential for harnessing solar energy for computing is something worth exploring. It's also important to remember that different types of native computing, photonic, quantum, and neuromorphic, are at different stages of development. Photonic computing is probably closest to practical applications, while quantum computing is still largely in the research phase. The future of computing is likely to be a mix of different... Okay, so we're going to go... Okay, so I'm going to go to my next question. Due to the sun's unpredictable fluctuations and weather, would the sun create difficulties for this technology? And then she says, yes, you're absolutely right to point out the sun's unpredictable fluctuations and weather as significant challenges for any technology attempting to directly utilize it for precise operations, especially in something as delicate as advanced computing. Here's a more detailed look at those difficulties. Intensity of fluctuations. So I know all this, but sunspots, we go. Weather dependence. Okay, so then spectral changes. Okay, so I wanted to get to my next question. It goes on for like 10 more paragraphs. Thermal. Okay. Energy storage. Okay. I'll just skip past the summer. Okay, so then I said, it sounds like the artificial light sources will be much more reliable and stable. Will the sun interfere with those systems? And then she says, it's a great question. While the sun interferes with light-based computing systems that use artificial light sources, lasers, generally no, but then she goes on to talk about different frequencies, and what I was more interested in is the low frequencies, not, the non-visible frequencies. Okay, so I'm scrolling through about 10 more paragraphs that she said. Very great information. So then I said, thank you. Yes, I was thinking more about the wavelengths emitted by the sun that are able to penetrate shielding and are not necessarily visible to the human eye. And then she said, you're absolutely right to be thinking about the broader electromagnetic spectrum beyond visible light. Even if shielding blocks visible sunlight, other wavelengths from the sun could potentially cause interference. Here's a breakdown of the considerations. Infrared. Sun emits infrared, blah, blah, blah. We know what that does. Ultraviolet, blah, blah, blah. We know. radio waves, while less connection for light-based computing, which uses much higher frequencies. Radio waves from the sun and other sources could potentially interfere with electronic control systems. Okay, we know all this. And the X-rays, we know that. How to mitigate material selection, shielding. Okay, we already went through that. Long. Okay. Oh, and then she put, important note, the level of concern about non-visible light interference depends heavily on the specific design of the light-based computing system and the materials used and the environment in which it appears. For most indoor systems, the risk is relatively low. For outdoor space, okay, and then I knew that, that I'm not talking about indoor systems, obviously. Okay, so then I said, so I was thinking, if light is a future for technology, we could create something that would block the interference from certain wavelengths created by the sun. As you said, it's not much of a problem for controlled environments, but if this technology is to be successful, it will also have to be available outdoor and in space environments. And then she said, you're absolutely on the right track. If light-based technologies are to thrive in diverse environments, including outdoor and space settings, effective ways to manage solar interference, including non-visible wavelengths, are essential. Here's a breakdown of how this could be approached, and this is what I was looking for the whole time. Advanced shielding materials. Selective blocking. Materials could be developed that are highly transparent to the specific wavelengths used for the light-based technology, but highly reflective or absorptive to unwanted wavelengths, IR, UV, parts of the visible spectrum. Adaptive shielding. Imagine materials that can dynamically adjust their transparency on the intensity and spectral content of incoming light. Gosh, I'm losing my I'm losing my spectral efficiency. Okay. Effectively turning out unwanted interference. Nanomaterials. Nanotechnology could play a role in creating extremely thin and lightweight shielding materials with precisely controlled optical properties. Sophisticated optical filtration. Tunable filters. Filters that can be adjusted to block specific wavelengths, allowing the system to adapt to changing solar conditions. Multi-layer filters. Combining multiple filter layers, each designed to block a different range of wavelength, can provide the very precise spectral control. Holographic filters. Holographic filters could be used to selectively block or redirect unwanted light while allowing desired light to pass through. 3. Wavelength selection and conversion. Optimal wavelengths. Choosing wavelengths for the light-based technology that are less abundant in sunlight or affected by atmospheric absorption can reduce interference. Wavelength conversion techniques. To convert incoming light to a different wavelength that is less susceptible to solar interference could be employed. Active interference cancellation. Generating counter signal systems could be developed to detect and analyze incoming solar interference, and then generate counter signals that cancel it out. This is similar to noise-canceling headphones. Number 5, adaptive optics. Compensating for distortion. Adaptive optics, which are already used in astronomy, could be used to correct for distortions caused by atmospheric turbulence or other factors, improving performance. Space-specific considerations, we'll just skip that one. Integration in systems design. Holistic approach. Combining these different techniques in integrated ways would essentially be creating robust, reliable, light-based systems for diverse environments. Systems optimization. Careful design. Okay. Important note. Specific techniques used would depend heavily on type of light-based technology, the environment which it operates in, and blah, blah, blah. Okay, I think that might be the end for now. Holy cow. Yeah, so basically, I was just trying to find out what's in the chemtrails and why, and I guess we found out, didn't we, Rue? We just found it out. Thanks, AI.